Good morning. I think I should say good afternoon. For me, it's good. It's evening. And I will talk about our performance benchmarking and tuning for container networking on ARM, which is about our work on the performance benchmarking issues. For this slide, I would like to introduce for this following agenda. First, I will give a brief introduction about the topics, and then I will talk about the container networking interfaces on ARM. And it is the core part of the benchmarking metrics and the environment and the tools and the benchmarking results. Actually, we could like to present some initial performance analysis with the perf tools, and we would talk about some future work consideration. Firstly, we would introduce what is CNI. CNI is a container networking interface. It's a cloud-native computing foundation project. Consists of a specification libraries for writing plugins to configure network interfaces in Linux containers, along with a number of supported plugins. And for the right part, it's a CNI plugin, CNI plugin graph, which shows the CNI part, and which connected to the Kubernetes runtime, which is Kubernetes to create a new container and delete a container. It will call the CNI plugin to create the pod or create the container. For the Kubernetes networking mode, we have several assumptions. First one is that all ports can communicate with other ports without using the network address translation. And the second one is all nodes can communicate with all ports without NAT. And the third one is IP that port sees itself is the same IP that others see it as. So it's I think Kubernetes networking model is a virtual networking environment for virtual networking environment for the Kubernetes. And actually, we have the following CNIs as I had listed in the red part, and but not limited to, because there are so many CNIs here that we could talk about. So, but we can only touch only a very small part of them, because there are so many complex CNIs, many which each one provide very senior features, very good features, but very good solutions for container networking. But we can only choose a few, very few of them to talk about. You may be interested in what we have enabled for the on the ARM platform for the CNIs. Actually, we had enabled the following one on the ARM platform and integrate them into the Arduino IC ARM edge stack as a reference. The first one is Calico, and the second one is Cilian, and the Contiv VP, and OVN Kubernetes, and the SRV CNI, and Flannel. We had listed the features, each one. For example, Calico provides pure IP networking fabric, which can uses the overlay-based solution or the direct routing-based solution for the container collection. For Cilian, it is a Linux native API-aware networking and security for containers. It uses the eBPF-based network policy for load balance, for security, and all things like that. Another widely used CNI is the Flannel. Flannel is very easy to deploy and is a very simple solution for the Kubernetes networking. So it is widely used as a demo purpose. For the demo purpose. And for SRV, it is a physical network interface support for the pods. And for OVN Kubernetes, it's a OVS-based Kubernetes solution. Here we just talk about 3 CNIs in this this slide. The first one is Flannel. Flannel uses an overlay solution for the port-to-port communication across hosts. Here is the architecture for the Flannel, which uses IP and the VX line as the backend. The second one is Cilium. Cilium uses almost the same overlay-based solution for the cross-host communication that uses a Cilium host to collect all the port to the host and use the Cilium VX line to collect it to the outside world and to for the inter-host communication. And here's the basic networking architecture for Cilium. Cilium also support the direct routing mode, but we had not touched it because, but we had not tested it until now. And the third one is Calico. Calico is a high-performance networking solution with the direct IP networking fabric. And actually, for the routing-based solution, it can support no encapsulation-based solution for the port-to-port communication for the inter-host case. And for Kubernetes service, the basic solution is from the Kubi proxy, which uses IP tables to support the load balance and for support the load balance for the different back-end boards. And another a recent solution is from the eBPF support based solution. For example, Cilium and the newest the current Calico also supports the eBPF based solution, which has much better performance than IP table solution. Actually, we should talk about our benchmarking metrics environment and tools here. First one is that we want to talk about TCP and the layer 4 performance and the layer 7 performance, which is about HTTP. For the TCP metrics, we talk about bandwidth. We talk about bandwidth in megabits per second or gigabits per second. And for HTTP performance, we talk about bandwidth in megabit per second and gigabits per second and CPS RPS. But we have not listed out the CPS RPS result here for the. Actually, we don't have too much time in this topic. We use this IPerf for the TCP IP performance, TCP throughput, and we use this WRK client, WRK as the HTTP client to do HTTP metrics here. Here we got a 10 gigabit collections for the cross-host inter-host communication for the pod-to-pod or node-to-pod. Actually, we had uses ARM server here, which is from malware, and we don't talk about the details. We want to talk about the type of this machine because of our test result is so maybe some a little sensitive. So we would not talk about the concrete solution, concrete platform. And actually, this is the collection topology for IPerf test and the WRK HTTP test, HTTP performance test. And the first one, we will collect the IPerf client to the IPerf server. Each one runs in a pod. The second one would be we will use Nginx as the HTTP server, and we would use WRK as the HTTP client. And for the WRK, we use two types of tests. First one is we run WRK on the host from another host. The second one, we run WRK in a single pod. So there are two cases here. This page also gives out the collection between the pod to pod and for the interhost and intrahost intra-host cases. We would like to present the benchmarking results of TCP throughput for the CNIs with different backend. Here, the first one we would like to give out is that we would give out the node-to-pod TCP performance, and there's several test cases for I would like to list it out. Is the first one is IP from for the Calico IP overlay solution from Calico, and the IP solution from Flannel, and the VXLAN solution from VXLAN backend of Flannel, and the VXLAN solution, VXLAN based solution for Cilium. And also we want to check then about the what is the result what is the result would be for the direct routing. We just use the Calico direct routing, which has no tunnel for the pod-to-pod communication, which should be directly fill out intrinsics, and we should think it should have the best performance. Actually, from the performance from these two graphs here, the first one is the node-to-pod performance, and the second one graph below is for the pod-to-pod performance. You could look at the page here. Actually, I would like to figure out what are our observation for the TCP performance over different CNIs. The first one is that the performance gap between CNIs are not so explicit when the overlay tunnel is used. And for the Calico and the Flannel shows a little bit better performance than Cilium for most MTUs here. Actually, we had set different MTUs for the physical NIC and for the virtual interfaces to collect to the pod, and the virtual interfaces for the different bridges we used. So we would match then. So the MTU we used is from the 1500 to the line 1000, and you can check the step we increase the MTU. And for the Calico and Flannel shows a little bit better performance than Cilium for most MTU scale. And with IP and the VXLAN overlay tunnel enabled, the large MTU size, the throughput performance is better. When you use direct routing, the throughput performance is not so significantly affected by the MTU size. So you can see that even with a very small MTU, such as 1500, we still have good performance compared to the large MTU. We don't lose explicit performance here. And the performance of direct routing here by Calico is better than IP enabled. So actually, the direct routing shows much better performance for the IP tunnel and the VXLAN tunnel, which is an issue we are investigating. And the IP tunnel is a little bit better than the VXLAN tunnel. In general, the node-to-pod TCP performance is better than that of pod-to-pod, which flows one more step because of the VTH collection to the Linux kernel for the pod. Finally, compared with different scenarios, it proves that IP or VXLAN overlay tunnel, which are now implemented in the Linux kernel, is a key fact which affects the performance of CNIs on ARM. Here is a very interesting question: is that why the node-to-pod performance is no better than that of pod-to-pod case for Cilium? It's a little bit strange here, and you could think it further, and we still have no direct answer on it. This is for the HTTP performance benchmarking for Calico CNI. And we would just give out we would just explain what it talk about. We use different file sizes. The file size is from 600 bytes to 500 megabytes. So if we increase the file size, at the same time, we also increase the MTU we used. And so the MTU is from the 1500 to 9,000. Actually, you see very strange values here. For example, the 1480, which means that we uses because IP overhead payload overhead is the payload overhead is 20, and for the VX line the payload overhead should be 50. So we should decrease the payload overhead. Decrease the payload overhead here. So we got a very strange value here, but it will not affect the result. And here you know what we are talking about, and you could give some out our initial observation here. Actually, MTU has a rather big effect on the performance when accessing large files, but when the accessed file size is small, it has little effect. The accessed file size is a major factor to the HTTP performance when there is only a small number of parallel threads. When the file size is big enough, the performance can't be improved much, even with big MTUs. And the second one for the HTTP performance testing is that for the pod-to-pod HTTP performance with the Calico non-IPIP overlay for cross-host communication. Our initial observation is that almost the same as that of IPIP, and the file size has much more significant performance impact than the MTU. For file size is greater than 10 megabytes, the MTU has little effect than to the final performance. The performance is much higher than those of IPIP when file size is greater than 100 kilobytes. You could see from the next page. You could see from the next page. And the HTTP performance benchmarking here, HTTP performance, this is for the third one. Third one is that pod-to-pod HTTP performance with Calico IPIP versus non-IPIP cases for cross-host communication. Our observation here is that for file size, which is greater than 10 megabytes, the MTU has little effect to the final performance, and the performance is much higher than those of IPIP when file size is greater than 100 kilobytes. And when the MTU is small, the performance gap between IPIP and non-IPIP is higher. Here is the host to pod and VS versus the host to service HTTP performance with Calico IPIP and non-IPIP for cross-host communication. Our observation is the performance gap is minor when accessing small files. For small file size, the host to pod and host to service performance is almost the same, which means that the service accessed by IP tables is not the bottleneck for the HTTP service. The performance of non-IPIP is much higher than those of IPIP when file size is greater than 100 kilobytes. And for large MTUs, large file size also support performance better than host to service. And for non-IPIP, the performance gap between different MTU is not so explicit. So it's believed IPIP is actually the bottleneck, which is the same as previous. And we would like to compare different CNIs. I will just give out the HTTP to service cases for different CNIs. And you could take from this graph, you can see that for the three CNIs, the performance gap is minor when accessing small files. As previous, direct routing mode shows the best performance with any other compared with any other overlay-based solution approaches. For file size, which is greater than 100 kilobytes, the Calico shows explicitly the best performance over other two CNIs, and the Flannel shows the worst host to service performance. And for large MTU and large file size, CDM shows similar performance with the Calico CNI. For long IPIP cases, the performance gap between different MTU is not so explicit. So it's believed that the tunnel communication is actually the bottleneck, which is the same as previous. We would like to give some initial performance analysis for the overlay-based solutions for the pod-to-pod communication to find out what's the bottleneck here. But we only got the previous result. We could have used the performance tools such as ftrace, perf, dtrace, and something like. Here we just give the perf. We can use the perf and with the flame graph package to go to the flame graph for the perf test with and without the IP tunnel. Here is the flame graph to the IP tunnel case and the no tunnel case. You could see for the IP tunnel case, the CPU takes takes two-thirds of the time for the idle in the idle state. It cannot in the whole state for the non-tunnel cases. For the non-tunnel cases, the CPU can use this. Or most of the CPU are used on the transmission and the receiving. We also used on the receiving. So we should find out the final root cause for the problem in the late time to investigate why the CPU is in the idle state. So here we are our brief summary. Here brief summary we got, and for the benchmarking case, and we think all the three CNIs utilizes the Linux kernel overlay tunnel implementation to enable cross-code support and service communication. And the TCP throughput performance gap between CNIs are not so explicit when overlay tunnel is used. For TCP throughput, Calico and Flannel show a little bit better performance than Cilium for most M2 here. But with IPv6 overlay tunnel enabled, the large M2 size, the throughput performance is better. The overlay tunnel approaches and actually affects the performance either TCP or HTTP performance much compared with direct routing. And for HTTP performance, the Calico and Cilium shows much better performance over Flannel CNI. This is about our future work and which is provisional. For example, we do more performance testing for supporting the CNL features of CNIs. For example, the could be proxy replacement with eBPF for Cilium CNI and the encryption added cases for port-to-port communication, and eBPF introduced for Calico CNI, all things like that. And here is my topic for this, my slides for this topic. Yes, I think the time is up.